Welcome back to the second part of the Chemistry Chapter 1 material, and this part will include the measurement information such as working with units and significant figures and scientific notation, all sorts of math-related items. This starts at the bottom of page 2 of the handout that went along with Chapter 1, and now we're going to take a look at the remaining portions of the PowerPoint. If you didn't already view the information about how to navigate through the PowerPoint, if you decide to go through it on your own, please watch the previous Chapter 1, Part 1 presentation. All right, here we go. Measurement. Well, every measurement is composed of a number and a unit, and the number is meaningless without the unit. The proper aspirin dosage is 325. Okay, well, 325 milligrams or pounds? What are we talking about here? A fast time for the 100-meter dash, 10.00. Is that in seconds or days? Hopefully in seconds. The American system uses units like feet for length, gallons for volume, and pounds for mass. The metric system uses units like meters for length, and volume will use liters, and for mass we'll use grams. The metric system is definitely the system that I prefer and the majority of scientists prefer. The reason for that is it's just based on units of 10, and that meters, liters, and grams, all the differences between whether we're talking a little bit of length or a really huge length, all of those will still involve the term meters. Instead of talking in terms of miles, inches, yards, feet, all these different words for that, we have the same, we that love the metric system have the same base units for all distances in terms of meters. And just a quick aside, the reason why the Americans are still using the what I call the American system, it was originally the British system, instead of like the rest of the world, is because of pirates. Way back when, there were people in charge in the American government that said, hey, we want to switch over to the metric system. So they contacted the folks in France, and the French said, sure, we will send over someone with just a few tools that are necessary. In fact, they still have the original material that was used for the metric system, and they sent someone over with some copies of that. And on the way to the States, their ship got hijacked by pirates. So that particular Frenchman never made it to the United States. By the time the French sent over a second representative, the people in charge in the United States were no longer interested in switching to the metric system. And so here we are, still stuck with using just random numbers, the 12 and the 16, and all of that stuff is so different than the metric system. And it's frustrating to have to teach both to everybody, but here we are. Oh, ounces, that was another one. Okay, so here we go. In the metric system, each type of measurement has a base unit. Those base units include meter, gram, liter, and second. Now the second, of course, is the same whether we're talking American units or metric units, one we don't have to worry about, but the rest are different. The symbol for meters is the lowercase m. The symbol for gram is a lowercase g. The symbol for liter is a capital L, and the symbol for second is a lowercase s. Other units are related to the base unit by a power of 10. The prefix, the first letter, or the first part of the word that comes before meter, gram, liter, that indicates if the unit is larger or smaller than the base unit. And so you might have heard of gigawatts or gigabytes. That's with a capital G, and that's a billion base units. So a gigabyte, BYTE is computer speak, And a gigabyte then would be a billion bytes. Megabytes, or I don't know, megawatts, again, that's a million. Kilo, we will use quite often. And kilo, such as a kilogram, or the kilometer, we pronounce kilometer, those units are 1,000 times greater than the base unit of a meter. And just to give you a feel for the size of a meter, if you don't already know, imagine 3 feet. That's approximately the same length as a meter. 1 yard is about the same as 1 meter. So 1,000 of those creates a kilometer. And that's why we use kilometers in respect to miles in the American system. Deci, we probably won't use too often. They're kind of skipping through some of the common ones. But centi, like a centimeter, that one we use fairly often. And definitely milli, milligrams, milliliters, those get used quite often. Then micro, when we're starting to talk about a microscopic scale, we can work with that one. It would take 1,000,000 of the micrograms to equal 1 gram. And nano, meaning a billionth. This is, we'd need 1 billion of nanometers to finally be the distance of 1 meter. I'm not a big fan of how the smaller values are listed here on this page with the centi and the milli and micro and nano. You might have noticed that when I described them, I didn't say that I took 1 meter and cut it up into 1 billion parts to get down to a nanometer. Instead, what I said was that I would need 1 billion of these teeny tiny little nanometers to make 1 meter. That's often how I think about them instead. The idea that I would take a lot of the little guys to make 1 big guy. Scientific notation. You may or may not remember having learned scientific notation. A lot of folks need review with that, so we'll be going over that. But what you'll notice is, in a lot of ways, it's the zeros. So in this particular giga value, there are 369 zeros and then 1. The scientific notation is 10 to the power of 9. The one down below with nano at the other end, there are not 9 zeros, unless you count the one in front of the decimal point. There are 8 zeros, 3, 6, 7, 8, and then the 9th number is the 1. So if I see a small number that has a negative exponent, I know to put 1 less than that, so 8 zeros, and then a 1 or 5 or whatever it is that's being multiplied by the 10 to the power of a negative number. We'll go over this some more, but that's just a nice little shortcut for that. And okay, they gave us a few little footnotes down here. They're pointing out the fact that if they do it in threes, kind of like we do 3 zeros and then we put a comma if we're going in front of the decimal. If we're going behind the decimal, they're showing that it's common practice to put 3 zeros, then a space, or whatever the numbers are, and then 3 more, and then a space, and so forth, instead of having commas. There are a few units that are going to be in with the Greek symbols, such as the micro unit. See how it kind of looks like a U, but technically it's the Greek letter mu, which is a lowercase m for them. Anything else? Okay, so stay tuned for scientific notation and enjoy the fact that we can convert between all these teeny tiny sizes and bigger sizes just by using prefixes and multiples of 10. The way I do this, again, when I do metric conversions, I always say that the bigger units gets the 1. The idea that a lot of the little units are needed to make 1 larger unit. So when I think of a kilometer, I think of it as 1,000 meters to 1 larger kilometer. 100 little centimeters will be combined to equal 1 meter. One thing to help you with centi is the idea that a century is 100 years. There's 100 cents in a dollar, so centi represents the number 100. 1,000, you're going to want to remember that. We use milli a lot. 1,000 millimeters is equal to 1 meter. Let me point out to you that notice how if I'm just doing meter, it's just one lowercase m. If I'm doing millimeters, then it's 2 lowercase m's. 1 meter, 2 m's millimeter. And that's takes 1,000 of those to equal 1 meter. And then finally, 1 million micrometers with that micro symbol that looks kind of like a U, that is equal to 1 meter. We talked about mass before. We're going to talk now about measuring mass. Mass is a measure of the amount of matter in an object. It's similar to weight. The difference is that weight is the force that matter feels due to gravity. Instead of talking about things weights, because in theory, for example, my mass will be the same whether I'm here on planet Earth or if I go to the moon. My mass, however, will change. There's a lot less gravity, 1/3 the amount of gravity on the moon. So if I need an easy but expensive diet, I can just head on over to the moon and suddenly my weight will be 1/3 of what it was here on Earth. But my mass will still be the same. The kilogram is the kg. Again, that will be 1,000 of the smaller grams. And then 1,000 little tiny milligrams will equal 1 of those grams. Volume, that's the measure of the amount of space an object occupies. Liquids and solids with irregular shapes have volumes measured in liters. So we'll do some examples in lab. We're going to measure the volumes several times for different liquids, and I'll teach you how to measure the volume of a solid that has an irregular shape, something I couldn't use a ruler to measure. And these are known here on the left as graduated cylinders. They're cylinders because they have a cylindrical shape, and they're graduated because they have marks on them for us to measure the amounts. And there's beakers, the words that we use for the bottom right-hand side. A less accurate way of making measurements. It's great if you want to just get a general amount of a liquid. 1 kiloliter, KL, is 1,000 liters. 1,000 milliliters will then make up 1 liter. It's written as little m, big L, just so that people don't get confused as thinking it's a number 1. Solids with regular shapes, like a cube or a cylinder, they have volumes measured in base unit meters cubed. That's because we can measure the length of the cube, let's say, times the width times the height. And there's a separate formula for getting the volume of cylinders. If I was measuring in centimeters, then I would have centimeters times centimeters times centimeters for my length, width, and height units, and that would then be centimeters cubed. Volumes in liters can be converted into meters with this really cool fact that 1 milliliter is the same as 1 centimeter cubed. That also gets abbreviated to 1 cc per centimeter cubed. And here's the cool thing. So I grew up with the TV show ER, not grew up, but in my middle years, there was the TV show ER. And I always wondered when they would yell out that they needed 10 cc's of O-neg stat. And of course, eventually I learned that O-neg was a blood type, but it was much, much later that I finally realized that 10 cc's was the same as 10 milliliters. And then I could really imagine how much the volume is because I'm used to measuring 10 milliliters in the lab all the time. But that was my aha moment that 10 milliliters and 10 centimeters cubed, or 10 cc, exactly the same thing. And there's the syringes that could be measuring the 10 cc's or 10 milliliters of blood or some other liquid. Any questions? Okay. I miss being in front of the classroom because, again, I went to school to be a theater major, and I'm supposed to be up there doing, walking around, making eye contact with all of you. So I do miss that. Hopefully I'll get to see some of you soon in some live sessions. All right. Here are our conversions between English units, or what I call American units, and the metric units. So I will have a few problems where you're going to practice going between these two types of units. And yeah, I mean, look at all these numbers on the screen. It's just daunting to me to go from just M, KM, G, KG, and suddenly having all of these random numbers that are on here. If I need you to do conversions between these, since it is an online class that's essentially open book, then I'm going to expect that you're going to have access to these. It is something that you could, if I remember, I will put one up on, or you can remind me to put one up on Moodle that you could print out, or you could take a picture. Well, you're not supposed to use your phones on the test. Anyway, you'll be able to practice with these. Definitely you'll want to use these when you're doing your homework on Connect. Now we're going to talk about significant figures. So hopefully you're good. If you need to, take a break, start taking a look and make sure you understand the idea about the meters and liters and grams and how there are relationships that are very general, but relationships between the metric units and the English/American units. Because now we're on to something that's probably brand new to you. And I was explaining this to my roommate a few days ago, and she was like, why do we have to do this? So it's something we do in science, and I'm not going to be extremely picky like I used to be, but I'm going to need you to keep this information in mind. And there will be questions on this. I'll just try to make them not be huge values on exams. Definitely the first test. And there will always be a little bit of points counted for significant figures. So take a breath, and here we go. Exact and inexact numbers. An exact number results from counting objects, or it's part of a definition. For example, hopefully you still have 10 fingers, maybe you still have 10 toes, and we have the definition that 1 meter equals 100 centimeters. In theory, if you have exactly 10 fingers and not like 1.5 from a machining accident, and exactly 10 toes, I could in theory say 10 point and then an infinite number of zeros after it. Same with 100 centimeters. I could go 100.000 to infinity, or 1.0 to infinity meters. So with these exact numbers, there's no special measurement involved, and an infinite number of zeros could be tacked on after a decimal point. An inexact number results from a measurement or something that we're observing, and it will contain some uncertainty. There's going to be a point where everybody agrees, for example, that it's 15 centimeters. But then there might be a little bit of disagreement about whether it's 0.3 centimeters, 15.3, or 15.2, or 15.4. Just depends on the person making the observation. Or if it's in, say, a scale that you're using for measuring the mass of something, the scales will be making an estimate. And sometimes you can actually watch the last value kind of cycling up and down, and then maybe the scale will finally, I know my scale, for example, will cycle up and down for a little bit, and then it will choose one, and the screen will freeze on that value. What it's done at that point is estimated the last value. And that's where the uncertainty comes in. Won't be a massive one, but a little bit of uncertainty. Okay, so that's what an inexact number is. Significant figures. These are all the digits in a measured number and one estimated digit. That one where you kind of went back and forth and then decided, nope, I'm going to stick with this value. That's your estimated digit. You only get one, but it's there. This person is reading the volume of a liquid in that graduated cylinder. So we've cut off the bottom base part. And what they've done is they've come down to eye level with the top of the liquid that's in the graduated cylinder. We're going to talk some more, and you're going to watch a little video about this in lab. But the rule is when you're using a graduated cylinder, you have to look at the bottom of the curve. So I think you can see my mouse here, where that dashed line is from her eyes measuring it. She's measuring at the bottom of the curve, not where the liquid touches on the sides. And this has been marked as 32.0. Again, you're going to get more practice with this, but where the long line is at the 30, that's 30 milliliters. There's 9 more lines between the 30 and the 40. So each one is worth each one is worth 1. So we have one line, 31, and then where the bottom of this curve is, it's 32. This person said, wow, it's dead on that line. So this is going to be 32.0. Now someone else may come around and say, oh, I don't know, it's a little bit under. And they might say 31.9. Someone else may say, oh, I don't know, I think it's a little bit above. So 32.1. We all agree it's 32. It's just a matter of whether it's a little bit above or a little bit below. And so there it is, what I just said. We may all agree that the volume is close to 32 milliliters, but some may decide it's closer to 31.9 or 32.1. The last digit is estimated because we may observe the volume as being slightly different. This last digit is still considered significant, however. So the last digit, while it's estimated or uncertain a little bit, it's still important. Determining significant figures. Well, the neat thing is all non-zero digits are always significant. Then there's some rules for when a zero is significant, and I'm going to try to give you a memory trick to help you with this. If I have a zero between two non-zero digits, like 104, the zero is significant. 29.05. We say that this number has 4 significant figures. The 2, the 9, and 5 automatically, because they're not zeros, and we'll include the 0 that's between the 9 and the 5. How many does this one have? Ever watch Dora the Explorer, where she asks the children a question, or adults that are watching, and then she pauses and she smiles, and her little monkey boots smiles, and then she's like, you're right. So I'm going to assume that you're right. And you said this was 1, 2, 3, 4, 5 significant figures. When it gets a little bit more tricky is whether the zeros at the end of a number are significant. So here's the deal. Whew, it was really hard. I mean, exhausting for me to type that decimal in the number 3.7500. I went to a lot of effort to type in that decimal. If I go to the trouble, or someone else goes to the trouble of drawing a decimal point in a number, then the zeros at the end of the number are significant. They really meant that this number was exactly 3.750, and then they decided that the last value was a 0 and not a 1, for example. All of those digits are significant because of the decimal. That includes the zeros at the end of the number. So again, this one will be 5 significant figures. How about this one? This one's a little trickier. Notice there's no numbers after the decimal point. It's just the unit pounds. 620 points is how we would read this. Whew, that point was exhausting to write down. That means that the 0 at the end is significant. This will now be 3 significant figures. All right, at this point, you're probably like my roommate going, who cares, right? Well, I'm going to say this and you'll see it again now, but I'm trying to keep you invested in this. Let's say I took the measurement of something and it was going to determine whether a bridge was going to stay up or whether it was going to collapse. And I said that, I took one measurement and then a second one, and I combined those two measurements in a calculation, and my calculator gave me 10 decimal places. Well, if I write all those down, it makes it seem like I had really, really, really great instruments for measuring those two distances. I was super duper accurate. But in reality, all I had was a ruler. So my ruler and my eyeballs measuring it could really only go to maybe 0.1 or 0.01. I couldn't go very far. It's not fair for me to report all of the digits that came out on my calculator after I did a calculation with those values. I was nowhere near as accurate as it seems when I put a bunch of digits down. I can't do that and still know that the bridge is going to be safe. I need to let people know that, I did a general type of measurement, not very accurate. By using rules related to significant figures, we make sure that the answers we provide are not more accurate than the measurements that we made. I'll write it again. I was about to say it again, but it's going to be written down in a second. So, all non-zero digits are considered significant figures. Zeros between those numbers are also significant figures. Zeros at the end of a number that has a decimal are significant. If they went to the trouble of including a decimal point, they want the zeros at the end to be considered significant figures. A zero is not a significant figure if it occurs at the beginning of a number before any non-zero digits. What helps me a lot with this is to think in terms of numbers. I'm sorry, not numbers, in terms of money. So in this case, it's too small for me to think of money. But I understand that instead of saying 245 or 2.45 or 0.245, I'm using those zeros at the beginning of the number to make sure that I'm only giving you a really teeny tiny amount. The zeros are holding the places so that nothing else goes there, but they're not significant figures. They're just placeholders. So the zeros at the beginning are not significant. We often put the 0 in front of the decimal just as a, hey, there's going to be a decimal coming up, especially if there aren't any zeros after it. It's really handy to have the guy in front. The only numbers in this that were significant were the 2, 4, and 5. The zeros before the 2 were not significant. They're just placeholders. How many significant figures are in this number? You're right. It's only 1. The zeros at the beginning of the number were just placeholders. They are not significant figures. At the end of a number with a decimal, without a decimal. At the end of a number without a decimal, no one went to the excruciating effort of drawing the decimal. So what they're saying here is we were positive that it was 2,500 something meters. And they're like, well, we think it was 2,570 meters, not 2,560 or 2,580. What's exact is the 2, the 5, and then the estimated digit will be the third one, the 7, as opposed to a 6 or an 8. The 0 is there to make sure that you're getting 2,570 not 257. This is when money really plays a role. I'm pretty sure you would not be happy with me if I only gave you $257 if I owed you 2,570. This number has only 3 significant figures because there were only 3 numbers and the 0 at the end was not significant because there's no decimal. How about this next one? No decimal. The zeros at the end are just placeholders. So this one has only 5 significant figures. There'll be lots of practice with this, but I hope the idea of the decimal playing such a big role into whether the zeros at the end are significant or not, I hope that helps. And I hope thinking in terms of money will help you whenever you need to work with these numbers that have zeros without a decimal. The 0 is only a placeholder in the cases on this page. Okay, I'm going to pause the recording for a second. I'll be right back. Boom, something new on the screen just appeared, right? So this is called significant figures. I'll call it a different worksheet, let's say. And it's not for homework or anything, but it is for extra practice before maybe you go and do your homework. And it's something I put together to try to help everyone with significant figures. There's a little bit more. So what we've covered so far is how to determine, looking at a number, how many significant figures are in that number. Now we have to learn about how to make sure that when we do calculations, our answers do not have more decimal places in them or more accuracy to appear in the answer than what we did in the original measurements. At the top, this is just to review whether if you have a decimal drawn, yes, then all the numbers after the first non-zero digit are significant. For example, 0.00040, because of the decimal, the 0 at the end is significant. The ones at the beginning are not, they're just placeholders. If there's no decimal drawn, any zeros at the end of the number are not significant, but the rest are. How do you know how many significant figures you should keep in your answers after doing calculations? First, you're going to need to know what highest place value means. That means that the thousands place is greater than the hundreds place, is greater than the tens place. Then the 10th place, one number after the decimal, is a higher place value than the 100th place, which is a higher place value than the thousandths place. And this is when it's really good that we're not in person because of the effects of. Okay, so hopefully that makes sense to you about the highest place value. We'll need that in a couple more minutes when we talk about adding and subtracting numbers. But in the textbook, and therefore in my PowerPoint presentation, we'll start by learning the rules for significant figures when multiplying and dividing. This is what we'll be doing 95% of the time, maybe even more. I mean, after the first test, I'm trying to think if there's any more about adding and subtracting numbers and thinking about significant figures. The majority of the time, we're going to be multiplying and dividing numbers, and you'll be using these rules. Here's the rule. The answer to a multiplication or division problem will have the same number of significant figures as one of the original numbers. It'll be the one that had the fewest significant figures. So 351.2 has 4 significant figures. How many are in 5.5, the other number in the calculation? Okay, I kept it easy for you. It only has 2, no worries about zeros. We do the calculation and the calculator comes up with all these digits. Again, this makes it seem like I had really fancy instrumentation that let me be super duper accurate, but I didn't. I was only able to measure up to 5½ hours, so maybe 30 minutes, not into seconds, for example. Therefore, my answer needs to be changed. I need to think about how many significant figures my final answer will have, and then I need to change this number to that. The rule, since we divided, is we can only keep 2 significant figures. Because of the numbers that we worked with originally, the fewest number of significant figures was 2. All right, so how do I do that? Well, I keep the first number starting at the left, the 6 for sure. I want that 6. Then I need to take a look at the 3 that's next to it. I want the second digit, I want the 3, but will it stay at 3? Let's take a look. We're going to keep the first 2 numbers. We're going to drop the rest. But before we say goodbye to them, we need to look at the guy that's right next door to the 3. If the guy right next door to the 3 is 5 or more, let me do it the other way, between 0 and 4, we're going to drop that digit and everybody else after him, and not change the 3. If the guy that's right next door is between 5 and 9, then we round up the last digit we're keeping by adding 1. In this case, 63.8. The 8 is 5 or more. So the 3, we add 1 to that. We round it up to 64. All right. Most of you will probably have done that fairly recently, but I work with students that are taking a test to get into nursing school, and some of them just need a little refresher with that. There's your refresher. And our final answer is 64 miles per hour. I'm going to do a quick thing just to make sure that I did this correctly. I'm going to say out loud. The original number was 63.85, blah, blah, blah. 63, 64, okay, we did all right. Had it been 630 and I ended up with 64, then we would have had a problem. If this had originally been 630 and now it's only 60 instead of 600, I will have made an error. It's always good to go ahead and double check, especially if the numbers are greater than 1. Make sure you haven't left off an important 0. The zeros can be important even if they're not significant. They have an important job as placeholders. Let's give these a try. We have 23.2 times 1.1. And I bet I wrote it this direction instead of the usual vertical way because I wanted to talk about significant figures. How many are in 23.2? You're right, it's 3. Oh, and 1.1 is 2. The calculator says 25.42, 25.52. How many significant figures do we get to keep? It's multiplication, so we keep the fewest number of significant figures. That one had 3, this one had 2, we only get to have 2. That means we'll start with the 20, the guy all the way to the left, and then decide about the 5. Will it stay a 5 or will it become a 6? It will be a 6 because the guy next door to the right was 5 or more. This one, 25.0 times 0.50. How many significant figures are in this 25.0? Drawing that decimal place was exhausting. So that's going to be 3. The 0 at the end will be significant because of the decimal. In this one, 0.50. Well, the 0 in front is just letting me know there's a decimal coming. The 0 at the end, however, is significant because there's a decimal. All right, so I've got 3 on the left, 2 on the right. Again, we'll use the calculator and see 12.5. That currently has 3 significant figures. It's too many. We're only allowed 2. So will this be 1, 2, or will it be 1, 3? Right, it'll be 1, 3, 13. Do I have any more? All right, so now, my class, I want you to round 8,534 to 3 significant figures. Currently it has 4. I need it down to 3. And I want you to remember, say the number to yourself before and after rounding. Would you be satisfied getting this amount of money? So you may want to pause it. I'm going to count to 3 and then we'll talk about it. So 3 significant figures. I'm going to start at the far left. I'll keep the 8 and I'll keep the 5. I'll take a look at the 3. The 3, should it stay at 3 or should it become a 4? Well, the guy to the right is only a 4. He's not 5 or more. So we're going to keep it 8, 5, 3. That will be 3 significant figures. But the original number was 8,534. If I just keep 853, that's only 800. Wow, people are going to be mad at me for only giving them $853 instead of $8,530. Whoops. So apparently I would be doing this on the calculator. Let's see. What can I do to make it appear? I can never see those numbers. I can do it if I do this. Okay. And so I'm going to write down that this should be, keep the 8, keep the 5. The 3 stays a 3 because it's only a 4 next door. All right. All right. 853. Not going to give you $853 and have you hunting me down. I will give you $8,530, and then I'm going to have to owe you the extra 4. I will not put a decimal. If I put a decimal, then the 0 at the end will now become significant. Then I would be back up to 4 significant figures, and that's not what I want. I want only 30. 8530, no decimal point, will be the final answer. Please ignore if there's a black box on your screen. It'll go away in just a second. Now, briefly, we're going to go over rules for addition and subtraction. Again, the previous rules, keeping the fewest total number of significant figures, that rule we'll use the most when we do multiplication and division. In the beginning, we're also going to do some addition and subtraction, just so you know there's a different type of rule. For this one, the answer will stop at the same place value as the number with the fewest place values. Okay, so this is where you had to remember about place values. In the original number, 10.11, the accuracy went all the way to the hundredths place, 2 places after the decimal. In 3.6, the accuracy is only to 1 decimal place. When I add them together, I get 6.51. This is too accurate, or I mean, it implies too much accuracy. We have to stop at the tenths place because our value stopped at the tenths place. And so this will then be 6 point, and will it be a 5, or will it round up to a 6? This is accurate to the hundredths. This is accurate to the tenths. Answer must stop at the tenths place. Then we'll get 6.5 kilograms. Our final answer that's accurate to the tenths place. Oh, and then I think I will do another example with you, and then I'm going to stop this recording and I'm going to start a new one just so that the new concepts will be on Now should I start a new recording? No, I'm going to keep going. Let's do one more practice with this though. To do that, I'm going to do a new share, which I think is Alt-Shift-S. And then we're going to my .cam. And voila. Let's try, so this is adding and subtracting. With significant figures. And we have the, what am I going to say? We're going to do 550 plus 21.0. No decimal. This is only accurate to the tens place. This one is accurate to the tenths place. Our answer must stop where? At the tens place. My answer cannot be more accurate than the measurements I'm doing the calculations with. This one's just saying it was 550 versus 540 or 560. I can definitely not have an answer that's more accurate than that. Okay, so without, this is what my calculator would put out. And now we're going to stop at the tens place. We're going to stop here. So I'll start with the 5 and the 7 right next door. It's less than 5, so we're going to keep it as 7. I'm not going to give you $57. I'm going to give you $570. That will be close to 571. This will be our final answer. It's accurate after addition to the tens place, just like the least accurate number that we worked with. And what did I say it was? Alt-Shift-S. Back to my regular screen. We'll have more practice with this in the homework. I tried to make it only maybe one homework problem or two instead of, and mostly multiplication and division practice. All right, next, scientific notation. Some of you may remember this if you had math fairly recently. Others, this may have been a while. And in scientific notation, a number is written as something like 5 or 12 or 268.9 times 10 to an exponent. This guy, they're going to call a coefficient, okay? A number between 1 and 9. And yeah, I was saying that wrong, wasn't I? Sorry. It can't be 12 or 569. It has to be just one number, but it could then be 1.29 or 1.12. That's what it is. Exponents. Exponents will be any positive or negative whole number. We're not going to work with fractions. Some may have done that because it turned it into square root problems. We're just going to work with whole numbers. If the original number is larger than 1, then x will be positive. So if the number does not start with a decimal, like 0 point or just point, then our exponent's going to be positive. If the original number is less than 1, so less than 0.9, then x will be negative. I say if the original number starts with 0 or a decimal, the x is going to be negative. I'd like for you to convert these numbers to scientific notation. I'll do the first one with you. We have 1300. My first question is, how many significant figures are in there? Because there's this really neat thing about scientific notation. Whatever numbers you see in scientific notation, they are all significant. And that's because a decimal is involved when we do scientific notation. That means the zeros at the end will be significant, and we don't start off with zeros in scientific notation. So it's a pretty neat trick. Here's what we're going to do. In both of these problems, we're doing them simultaneously. We move the decimal point to give one number between 1 and 9. So there's an invisible decimal here in 1,300. The invisible decimal point is at the end. We then swoop, swoop, swoop 3 places to the left, and we get a number between 1 and 9, the 1. On the right-hand side, we start with the decimal and we move it 1 place behind the first number that's not the 0. Then we're going to do times 10, and we're going to have an exponent. 1.3 times 10 to an exponent. X is going to be the number of places the decimal was moved. Now, honestly, I'm not a big fan of what they say in your thing. When it says move the decimal to the left, X is positive. In fact, you know how much I hate this? We're going to change that. This is what I'm talking about with where I change it from what the book said. It's not letting me do that. Isn't that funny? There we go. If the number was greater than 1, then X will be positive. If the number was less than 1, then X is negative. In this case, it was less than 1 to start with, so now we'll have 1.36 times 10 to the negative 1. The exponent number 1 is from when we move the decimal 1 place. With the other value, the 1.3 times 10 to the positive 3, that's because the original number was greater than 1, so we have a positive exponent, and we move the decimal 3 places. Notice that the zeros disappeared. These zeros were never significant. They were important, they were placeholders, but they were not significant, so they do not remain in our final answer. Scientific notation only includes significant figures. That's what I love about it. This guy, again, we lost the 0 at the beginning and are only left with the significant figures, the 1.36. It's a negative exponent because the original number was less than 1, and it's negative, for that reason, and we only had to move the decimal 1 place. The insignificant figures, the insignificant zeros were dropped. And so here's where I just reinforce that idea when the exponent x is positive. We're going backwards now. We need to make our scientific notations into what we call standard numbers, where we don't have the times 10 to a power of something. And if the x is positive, so we have a positive 2, that's going to tell us that we need to move the decimal 2 places to the right. Now, if you want, instead of getting confused with the whole left and right thing, which is what I tried to just get rid of before, you can think about the fact that when it's a positive number, it means we are multiplying by 10 that number of times. 2.8 times 10 would bring us to 8. Times another 10 brings us to 280. Now my decimal will be left, and we still have a 0 at the end of the number. Both of these zeros at the end were significant because there was a decimal. My final answer, therefore, will include both of those zeros. Every number in scientific notation is significant and needs to be included in the final answer. If I had 2.80 times 10 to the negative 2, a negative number is the same as dividing by 10. So if I divide 2.8 by 10, then I will get 0.28. If I divide it by 10 a second time, then I get 0.028. Because the 0 was in a number that had a decimal originally, it's significant. That means I need to continue to keep it in my final answer. The cool thing to remember, any digits in the scientific notation form must be significant. That's because there won't be any zeros at the beginning, and with the decimal, the zeros at the end are significant. Be sure to include all of the zeros when you convert numbers from scientific notation into standard form. Okay. I really am going to stop this recording now because we've played around with the numbers. We've learned about significant figures and how to write in scientific notation. Next, we're going to go into unit conversions, and I want to just keep that a separate video. If you have any questions, let me know. You also have the textbook to work with on all of this. So check out chapter 1, part 3, that I didn't know was going to exist, for me to tell you about how to convert between units. See you soon.